Hello, in the 12th video in my little mini series on Fourier series, we're going to look at Dini's condition and Jordan's condition. And both of these conditions are what are called sufficient conditions for convergence. So if these conditions are met, then the Fourier series converges to f of x. And that's what we're looking at today. So Dini's condition is the Fourier series converges to f of x if for some delta such that it's between 0 and pi, the following exists. So if this integral exists, meaning it's not infinity, then the Fourier series converges at x. Okay, so now for Jordan's condition, I wrote this in after I'd already started. I didn't think I'd have enough room or time, so I added Jordan's condition. But I need B and C to help me prove D. And I could get it all on 4 pages, which is sort of my limit for what a video should be, or at least, so it's not too long. So B is if h of t is a monotonic increasing function, which is 0 when you approach 0 from the right. And we're going to show that if delta is between 0 and pi, then this limit is 0. So from 0 to delta of this. And part C, which is the second part I need to help me prove Jordan's condition, let f of t have bounded variation, and the limit is 0 when t approaches 0 from the right. We want to show that when delta is between 0 and pi, this limit is 0. And then we're going to use these two conditions to prove Jordan's condition, which is another sufficient condition for the Fourier series to converge. And then I'll write out Jordan's condition on page 4. I didn't have room to kind of shove it in here, and I didn't want to rewrite everything. So Dini's condition is this. By F1, the Riemann-Lebesgue theorem, if this function is integrable in 0 to pi, then this is 0. And so what this is saying is, the Riemann-Lebesgue theorem says that if you have a function that's integrable, meaning it exists, and then you multiply it by sine or cosine, then that integral is 0. Okay, that's the Riemann-Lebesgue theorem. But this condition here is actually what we covered in F11 part F. It said that if this condition is 0, then we know that the remainder is 0, which then tells us that the Lebesgue or the Fourier series converges to f of x. So this is just that condition F11F. But in order for this to be true, we have to know that this condition is integrable, meaning that it exists. And that is the result we wanted to show. That if this condition exists, meaning it's integrable, then we know that this in limit goes to 0. And then by F11 part F, we know that if this goes to 0, the remainder goes to 0, which then tells us that the Fourier series converges to f of x. Now on to part B, we're going to prove these two conditions or theorems or corollaries about bounded functions. Well, this is monotonic and this is bounded. Both have limit at 0 when it approaches 0 from the right. So this one here, we're not going to prove, you know, it's always one of those things. When in proofs, how far do you go back? You know, so we're going to assume that you can look up the second mean value theorem. Some will call it the second mean value theorem for integrals. But this is it. So if we have some delta 1 between 0 and pi, this condition's true. And let me help go over this. So we're integrating from 0 to delta 1, and we know h is monotonic increasing. So if we just stick in the biggest value in here for all values in this range, this function just got bigger, okay? And so that's what we do here. So if we stick in the biggest value, it gets bigger. But then to make it smaller, instead of going from 0 to some number, we go from nu to some number. So like go up a little from 0, up a more. If it's still bigger, go up more. Oh, we went too far, come back down. At some point, these are going to equal. And that's what the second mean value theorem is. Okay, so this is one of those things that when you see the proof, you go, oh, yeah, that's right. And it's not too hard. But to actually do the proof on your own is not straightforward. So this is true for some nu such that it's between 0 and delta 1. Now let's let u be n plus a half t, and we do that to get rid of, you know, we're going to make a u substitution in here, and then the derivative, well, you'll see. So, and we're only going to make this u substitution for the right hand integral, so this piece here. Then, so this is this side, and this is this side with that u substitution. Now, if we look at this piece here, so these two are equal. The sign is a bounded function, and actually 1 over u is bounded on a given interval. And so this ratio is bounded for some number. And so that's what I'm going to claim, is that the right hand side is bounded for some number, call it capital M. And this M, of course, depends upon, you know, n, you know, the capital N, it depends upon delta 1, depends upon nu. So this may get pretty darn big. But at some point, there is a number bigger than what this is, and we're going to call that M. Now, since the limit is of h of t is 0 when we approach 0 from the right, we're going to pick delta 1 small enough such that this function is less than some really small number, epsilon over 2m. Now, right, so as t goes to 0, this goes to 0. So if we're approaching 0, at some point we're going to get less than this number here, and that's the number we want, delta 1. Then this integral is you know, that we're going from 0 to delta 1, but we're making this delta 1 that when we plug in delta 1, it's less than this. So let's stick in this bigger number for h of t, and that's what we do here. And then this piece is just the same. But over here we said that since these two are equal, this is bounded, which means that's bounded. So this is bounded by some number m right here. So we have epsilon over 2m and m, and this product is epsilon over 2. So this is bounded by epsilon over 2. Now n is, of course, can be quite large. So now by F1, the Riemann-Lebesgue theorem, this goes to 0. Okay, So here, these are both, this is monotonic increasing, this is, 1 over t. So these are integrable functions on this range from delta 1 to delta. And then take it times sine or cosine, that coefficient goes to infinity. Let n get really, really large. This goes to 0. So now, since it goes to 0, we can, at some point for some n, it's going to get really, really small. And it's going to be smaller than epsilon over 2. So we want that n. We want to be this n or bigger such that it makes this integral, which goes to 0, less than some epsilon over 2. So now for n sufficiently large, this integral, which is two pieces, it's from 0 to delta 1 and delta 1 to delta, and both of those are less than epsilon over 2. So this is, if we were to break it into pieces, is less than epsilon over 2 plus epsilon over 2, which is equal to epsilon. And this is a really small number. So as n gets large and we let epsilon go to 0, then this goes to 0. So we have proved part B. Now for C, we're going to let h of t be bounded, have bounded variation. And what this doesn't mean that it has to, well, it is bounded, but not every bounded function has bounded variation. It deals with how many oscillations that it has. And we want the limit go to 0 as we approach 0 from the right. And we want to show that this interval is 0 from 0 to delta. So now this is another one of those proofs. H of t, since it's of bounded variation, h of t can be expressed as the difference of two functions where h1 and h2 are monotonically increasing functions. And so basically what it's taking h of t, and you'll look this up. This is not a tough theorem to show, but if you look, kind of just type that in and it'll pull right up. You're going to take the h of t and decompose it into its positive components and its negative components, and then develop two functions like that when added you get h of t back. So that's really kind of what it's saying there. But h1 and h2 are monotonically increasing functions, and now since we assume that h of t goes to 0 as we approach 0 from the right, that means these two functions, the difference of these two functions, go to 0, which means they actually limit to the same value. Now, without loss of generality, we can assume that the common limit is 0, because if it's not, say the common limit's 5, then we can subtract 5 from this function, subtract 5 from this function, and then the limit of this is 0, and the limit of this is 0. And then it's like adding 0 to this. We add and subtract the same limit. So we're going to assume that this limit is 0. Now by part B, this is a monotonically increasing function that is 0 when we approach 0 from the right. So we know it's 0 from part A. And the same way with part h of 2. It's monotonically increasing. As we approach 0 from the right, it goes to 0. So we know this is 0. So if we take the difference of two functions that are, that limit to 0, then the difference is 0, and this is 0. But this original function is h of t. And so if we put in h of t here, then that's what we wanted to show. Right here. Okay, so now with those two proofs, let's look at Jordan's condition. Now, the Fourier series converges to the average of this. So this is f of h plus, so that means we're approaching x from the right side in limit. Doesn't say anything about the value of f of x. It's just the limit as we approach x from the right. And this is f of f minus. That says it's as we approach x from the left, what's the limit? And now if f is continuous, of course these two limits are equal. But if f is of bounded variation and in a neighborhood of x, then this is true, and I'll explain that in a second. So if f is continuous at x, of course, then the Fourier series converges to f of x. It means those two are equal. So you get two of them, and then the twos cancel, and you get f of x. Now, f is, it could be piecemeal. So this could be one function, and then it has a jump at here. So as we approach x this way, the limit is this, and then at x, it actually jumps up here and then goes here. And the Fourier series at x is actually the average of these two limits. Now, if f is continuous, it says that that it is equal to that. So that's what this says. Now, Jordan's condition deals with bounded variation in a neighborhood of x. In the next video, we're going to look at if we have certain requirements for f and the derivative of f. That is another way to show that the Fourier series converges to this average. But this is Jordan's condition when it just looks at bounded variation in a neighborhood of x. So, if x is of bounded variation, so is this function here. So f is bounded, and 2 times s, which s is this up here. So this is bounded variation. So when you're adding functions of bounded variation, it's still bounded, okay? So f of t is bounded. And now if we plug in what this means, okay, the 2 cancels here and we just get this. So it's f of x plus t, f plus f of x minus t minus f of x plus, which says it's the limit as we approach it from the right, and minus f of x minus, which is the limit as we approach from the left. So note that as we let t go to 0 from the right, it equals 0. So this is 0 as we go to 0 from the right. So as this is, we let t go to 0 from the right, then this piece is actually what this one says. So it's this minus the same value. And here, since we're going to t is going to 0 from the right, this piece is actually 100% like this piece. So we take this and minus the same value. So this is 0. And it has bounded variation. So thus, by part C, this goes to 0. Which shows that the Fourier series converges to the average of those two limit points. And I didn't actually write it down, but if those two limits from the right and the left equal, it's the same value. So you get 2 of those, and divided by 2, you get 1. So it is f of x. Well, that's all I got for today. Hopefully you enjoyed it. I sure did. Like the video and subscribe so you don't miss the next one. Thanks. Bye.